So welcome to circular motion. In this video we will look at the definition of uniform circular motion, which is the only type we'll be dealing with, and then the two velocities and the one acceleration that are associated with this type of motion. So uniform circular motion is defined, surprisingly, as motion that is both circular and uniform. So we have an object that is moving with a constant speed, orbiting around a centre point at a radius r. And the movement of this object can be described using one of two velocities and an acceleration. So the first of those velocities is the tangential velocity. And we know that the speed of the object is constant, but the direction of movement of the object we can calculate or we can find by taking a tangent to the object's path. So hence tangential velocity. The magnitude of the tangential velocity is the speed of the object, and it's given by the same formula as any object with a constant speed. So it's given by the distance covered by the object in a given time. And we know our object is moving in a circle, so we know that if it completes one orbit, it travels the circumference of the circle. So we know that the distance covered is 2 pi r, or the formula for the circumference of a circle. And we know, or we say, that that distance, the time taken to cover one orbit, one circumference, is the orbital period. The second way we can describe the motion is using something called the angular velocity. And the angular velocity is still a velocity, so it still refers to the rate of the change of the position of the object. But in this case, instead of referring to the change of position in meters, we're looking at the change of position in terms of angle. So to find the magnitude of the angular velocity, we're looking at the angle swept out by our object in a given time. And we use the same trick. So we know that in one orbital period, the object will rotate once, or will orbit once. And we know that in a circle there are 360 degrees, or 2 pi radians. So our angular velocity is given by 2 pi radians divided by our orbital time period. And from our tangential velocity equation, we can also see that our angular velocity is equal to our tangential velocity divided by the radius. And the final quantity associated with uniform circular motion is the acceleration. So we call this the centripetal acceleration. We know that the acceleration of an object is the change in its velocity over time. And there is a tendency to think of that as a change in the magnitude of the velocity. Certainly I do. And because when we use acceleration in a daily context, so when we talk about the car accelerating or decelerating, we're talking about the car going faster or slower. So we're talking about a change in the car's speed or in the magnitude of the velocity. But velocity is a vector. So a change in the direction of the velocity is also a change in the velocity and is also therefore an acceleration. So for an object undergoing uniform circular motion, the velocity is changing constantly. So the object is constantly changing the direction it's moving in. And that means for any object undergoing uniform circular motion, it must be accelerating. So as I said, this acceleration we call the centripetal acceleration. It's given by, the magnitude is given by the velocity squared divided by the radius. And the direction is always towards the centre of motion. So in the next slide, I'll go through the derivation of the magnitude of the centripetal acceleration. And the direction and the direction I will look at in the next topic, so under forces. So to derive the formula for the magnitude of acceleration, we'll start with a diagram. And the diagram shows our object, the Earth, at two different times. At time 1, it's moving with a velocity v1, and it's at a distance r from the centre of motion. And at time 2, it's moving with velocity v2. Also at a distance r from the centre of motion. Since we're looking for the acceleration, we want the change in velocity, and that we can find just by vector subtraction. So we take our velocity vector v1, we subtract v2, and the resultant gives us the change in velocity. From the diagram, we can see there's been a change in the position, so we can find the displacement of our object. So displacement is just the position at time 1 minus the position at time 2. We again do that by vector subtraction, and we get a similar triangle that shows our displacement. We know these triangles are similar And I won't derive it here, but I will provide you with a link under this video if you're interested in having a look. But because these are similar triangles, we know that the ratio of their sides must be the same. We're looking for the acceleration, which is the change in velocity over time, so we need to introduce time into our equation. So we divide both sides through by the change in time, and if we rearrange so that we get the acceleration term on one side, we get this equation here. So we know that our acceleration is equal to the change in velocity over the change in time, and we also know that our velocity is equal to the change in displacement over the change in time. So if we substitute these two values into that previous equation, we get the equation for our centripetal acceleration for the magnitude. And as I said, I will discuss the reason why the direction of our acceleration is towards the centre of motion in the next set of videos on forces.